Example 2. A steel white flange beam has the dimensions as shown in the figure. If it is subjected to a shear of V equals to 80 kN, plot the shear stress distribution acting over the beam's cross-sectional area. Right, so as you can see here in this figure, we are given an I section, right? Okay, and it is symmetrical, okay, on its left and right, okay, as well as for the top and also bottom, right? So we have a symmetrical arrangement of this beam, right? So of this I-beam, okay, with similar dimensions, okay, right? So we can see here, okay, from the figure, okay, we are given the dimension, okay, for the cross section of this beam as well as for the V value, right? So the V value for our case here is V equals to 80 kilonewton, right? So that would be the value that we are going to use in the calculation directly without having to draw or calculate the shear force value. Okay, right. So next we move on to the solution. So the shear stress distribution will be parabolic and varies in the manner as shown in the figure, right? So as what you have seen in this figure, okay, these are actually the stress distribution, okay, that has already been drawn and also calculated, right? So these are the values that we are going to actually determine, okay, from this calculation. So due to symmetry, only the shear stresses at point B prime, okay, and B and C have to be computed, right? So to show how these values are obtained, we must first determine the moment of inertia of the cross-sectional area about the neutral axis. Okay, working in meters, okay, okay, we can calculate the I value for the whole section, okay, and we are going to have the value of 155.6 times with 10 to the power of negative 6 meter to the power of 4, right? So this is for the moment of inertia, right? So as you can see here, as what has been mentioned in this statement here, since it is a symmetrical beam, right? So therefore, we are going to determine the values of the shear stresses only for the top parts, right? Because at the bottom parts, okay, we are going to have the similar values, right? So we can just ignore the values on the stress distribution first, okay, since we are going to look into how to calculate those values, okay. So first, okay, we are going to look into the points, okay, that we are going to determine the values, right? So the points, okay, that we are going to consider, okay, are the area A, okay, area A prime, okay, which is the area of the flange section, okay, which is this top part section. Okay, then we are going to have B prime, okay, which is located at the bottom of the flange, as well as B point. Okay, whereas we have another point that is in the uh, uh, exchange point, okay, between the flange and the web, right? So for point B prime, okay, tau B prime, okay, is equals to 0.3 meters, okay, as you can see here, this 0.3 meters is actually the width, okay. So we have this T, it is not tau, okay, it is T, right? So sorry, so T B prime is equals to 0.3 meters, okay. And as for A prime as well, okay, we are going to consider 0.3 meters as well, okay, right? So here, okay, based on this, what makes a difference, okay, in the equation, okay, so the basic equation of tau, okay, is equals to VQ divided by IT, right? So the biggest difference here is on the Q value, okay, as well as for the T value, right? So we have these two values, okay, that will vary as the location varies, right? So we are going to look into, okay, the area that we are going to consider and also the distance from the centroid as well as the thickness or width of the section, okay, right? So here, okay, we are going to look into QB prime, okay, which we are going to consider Y bar, okay, multiply with A prime, right? So as for this part, okay, we are going to consider the flange section, okay, whereas we are going to have the thickness, okay, of the flange section is 0.002, right? So that is the total width of the section. However, in the calculation of Q, we are going to consider the distance, okay, between the centroid of that particular segment to the centroid of the section. So as for this example, okay, we are going to have the centroid of this whole section is located right in the middle of the section, right? So it is an I section which is symmetry, right? So therefore you can see that the neutral axis is sitting right in the middle. So here we are going to determine, okay, the tau value of at the point B prime, okay, as well as the value of tau, okay, at B. Right, so it is actually of the similar location, only that one value, okay, will be using the flange, will be the flange width, okay, as well as the web width. Okay, so as for the tau B, okay, we are going to consider the web width. Okay, so we can see here, okay, that we are going to have, okay, the flange width, okay, for the tau B prime. Okay, so this is for the flange width. Okay, so that would be the T value. Okay, then as for the bottom part, another one, okay, we are going to consider the web width. Okay, right, so the calculation here will be slightly different. Okay, only that we can see here, okay, that the values of the shear forces, okay, are similar, okay, as well as for the value of the Q, right? So Q values, okay, for both cases, okay, whereas you can see here we are going to consider, okay, the area A prime. Right, so we can see that we are considering this equation. Okay, the calculation is shown here on top. Right, okay, whereas we are going to consider this area A that is shaded now. Okay, so you can see that I have shaded, okay, the area A prime. Right, so we can see that that is the area that we are going to consider in the Q calculation. Right, so Q is equals to y bar, okay, multiply with A. Right, so the area that we are going to consider is the area of the flange, then multiply this with the y bar value, which is the distance, okay, from the centroid of the A prime, okay, section to the centroid of the segment. Right, so you can see here, okay, I have already written, okay, the value of y bar. Right, so that is from the center of A prime, okay, to the centroid of the section. Right, so therefore you can calculate using 0.11 meters multiply with 0.3 times with 0.02 meters. Okay, so we have here 0.66 times with 10 to the power of negative 3 meter cube. Right, so that is the Q value that we are going to substitute, okay, into these two equations for tau B prime and also tau B. Right, so what makes the difference here, okay, is just on the values of tau B prime, TB prime, okay, as well as the value of TB. Right, so one is considering the flange width and another one is considering the web width. Right, so we have tau B prime is 1.13, and as for tau B, okay, the value is 22.6 MPa. Right, so we move on, okay, to the calculation. Right, so note from the discussion of limitations in the use of shear formula that is calculated, that the calculated value for both tau B prime and tau B will actually be very misleading. So why? For point C, right, so TC is equals to 0.015 and A prime, okay, is the dark shaded area shown in the figure. So considering, okay, this area to be composed of two rectangles, right, so therefore, okay, we can calculate okay, the value of tau maximum. Right, so we can see here that we can calculate the value of QC, okay, equals to the total of y bar times with A prime. Right, so we have a total of the flange, okay, as well of the area for the flange as well as for the area for the web. Right, so we can see from the figure here, okay, the shaded area, okay, that is the darker area in the beam, okay, is actually the value, okay, that we are going to consider in the calculation. So therefore, okay, the QC value, okay, will be of 0.735 times with 10 to the power of negative 3. But in the calculation, okay, of the tau maximum, okay, we can see that the difference that it will make here, okay, is not on the t value. However, the difference that it will make is on the q value, right? So you can see in comparison to the previous calculation, okay, for tau b and also b prime, okay, the value of this qb, okay, is similar, okay, whereas we have 0.66. However, okay, for the calculation of tau maximum, okay, you can see that the value has already changed to 0.735, right? So the difference is here, okay. But as for the TC value, okay, which is the thickness, right? So this, the thickness or the width of the section, okay, it is 0.015, right? So this is actually the web thickness, okay, or the web width, okay. So this is the web width, right? So what really makes the difference, okay, is the Q value, okay, not the T value, right? So therefore here we have 25.2 MPa.